construct the n+1 level of the structure. So n means we know a minus j for all j given n. And we know A0 Jn minus 1. Huh? Let me be more precise, because here is the delicate point. We know the Hilbert space Pk and the corresponding scalar products K for K less or equal than n. So this means that since A dagger J restricted to n minus 1 will go from Pn minus 1 to Pn. Pn minus 1 goes with the scalar product n minus 1. And this goes with the scalar product n, which is the last I have. So I have the adjoint of this, which is a minus. And remember that A minus J restricted to n minus 1 is the adjoint of AJ restricted to n. So, in this sense,
AJ minus restricted to n.
Okay, so A dagger goes from n minus 1 to n. So n minus goes from n to n minus 1.
Yeah, but the notation should be consistent. AJ minus restricted to n is acting on Pn. And you don't want n minus 1 to act on Pn, isn't it?
N.
Ah, yes. A minus J restrict. Yeah, we have this identity. A minus J restricted to n is the adjoint of A dagger J restricted to n minus 1. Okay, so this is the last. So what we have to do? We have to create we have to create this one is A plus J restricted to n minus 1 adjoint, which I have because I have the scalar product in n minus 1 by the induction assumption. Now I construct A dagger Jn algebraically by this prescription. If I know A0n, but in the induction assumption I have constructed A0j restricted to k for k less or equal n minus 1. So I have to choose the new A0n. And here comes the equation C2 inductive. So I have to solve this equation and pick one solution. Fortunately, this is a linear equation. Not all linear equations have solutions. But fortunately, I know that at least one solution exists. Because if I take A0 to be 0 for all k, for all restriction n, this is identically satisfied. So the operator A0, which is always 0, which will correspond to symmetric measure, is always a solution. This is an important point. You see, it's an important point in my attempt, and I hope you can help in this, to find what is the analog. If I have a two-state phi with omega n phi coefficient, and I have psi with omega n psi coefficient, then I say that psi phi is Jacobi equivalent to psi if and only if omega n phi coincides with omega n psi. The most important example is Gaussian. Gauss and Poisson are Jacobi equivalent, but of course they are very different. Huh? And my problem is how to define such Jacobi equivalence in the multidimensional case. We can discuss this in the open problems. There are some indications, but not a full solution of this. So it's a problem of, not a problem of solving an equation. It's to find the correct notion of equivalence relation which generalizes the one-dimensional case. This is not solved at the moment. So you see how little we know about this stuff. But let us go on and finish the induction. So now I have this. Since I have this, the inductive relation, I have this equation. Remember that we are n must be replaced by n minus 1. So here I will have the unknowns are a0j restricted to n as a function of a0j restricted to n minus 1 and a daga n minus 1, a daga n minus 1. So this I know, and a daga n I know because it's algebraic. In fact, this is n minus 1, so I even know by induction assumption. So I know everything is in this inductively. I know everything except the a0j n. I suppose that there is a solution of this equation. If there is no solution, what does it mean? It may be it's a linear equation, it has no solution. If there is no solution, it means I have to stop. What does it mean? What is the analog in finite dimension? The analog in finite dimension is that this Jacobi sequence stops at a finite n. And this is characterization of the measures with finite support. And this characterization is true also in the multidimensional case. Okay? So if I arrive that this equation has no solution, I have to stop. You see? And it's delicate the point, because you can imagine, in each step I choose one solution. So that is why it's important to have a theoretical knowledge of the space of a parametrization of solution. Because if I go just by induction empirically, by saying I pick one solution without knowing which one, I may stop. But I may stop because in the previous steps, I have made a choice which has led to a finite support measure. But maybe another choice may lead to a non-finitely support measure. Okay? So that is why it's so important to go deep and characterize the solutions of these equations.
So you made the statement that in one dimension, Jacobi sequences, it terminates to correspond to that the measure is finitely compactly supported or something?
The infinite dimension, the theorem is that if there exists n such that omega n is 0, the measure is supported in n plus 1 points. In here, we have not such an estimate of how many points there are. We have some estimates. Some young collaborator of mine made some estimates, but we have not a full analog of the finitely supported measures. See? Because the problem is that sometimes, well, this is another beautiful problem, to relate the dimension of the support of the measure to the rank of this omega tilde kernels. See? You intuitively guess that if a measure on RD, take R2, so take R2, and take a measure which is supported in the circle. So essentially, a measure in the circle is like one-dimensional case. And they have been very much studied. But how to recognize the analytical property of a support in a lower dimensional manifold from the rank? We know there is a theorem that if this omega tilde, in fact, the corresponding scalar product have rank n, have a finite rank d, or no, let's say d we already used, as a finite rank capital N, then all the next one will have the same rank. We cannot have higher rank. That we know, I repeat, we know later. But to complete induction, so now we have discovered, we have solved from the second induction constraint, for the second constraint equation, we have recovered A0JN. And since this is A minus, we know by induction assumption for this argument, then we can define a direct. So we can define the vector space. So the next open problem is to put the scalar product on this vector space. Here comes the first inductive constraint equation. I know that the imaginary part of this scalar product is this. Okay? So once I have fixed the A0JN, I have fixed the imaginary part of the scalar product. But the real part, and this is what I think is the real analog of omega n, the real part of the kernel is arbitrary. I can put arbitrary kernel. That is the analog of the fact that I can choose omega n arbitrarily, provided I have the constraint condition. Okay? That if one is 0, but this constraint is the same. If I choose one omega n to be 0, then there are theorems that I had no time to prove, but I put them in the lectures. That if I put one omega n to be 0, then all the norms starting from n will be 0. So the polynomial will be, the space will be finite dimensional, and so the measure will be finitely supported. Okay? So we choose a scalar, but the important point is that we can choose on the real part arbitrarily. So that is my conjecture, that the real part of the omega are the analog of the Jacob.
That's a conjecture.
It's a conjecture because in some sense, you see, the scalar product is defined also by the imaginary part. And the imaginary part depends on A0. You see? So the problem is, remember, the problem is how to define the multidimensional analog of this equivalence. So my conjecture is, of course, I can define that they are equivalent if they have the same real part of the scalar. This will be unacceptable, and that will be fully analog to. But we have to remember that it is true that a positive definite kernel, if I add a skew adjoint kernel, it remains positive definite. But the scalar product changes. It's not the same. So another equivalence relation might be that the two are equivalent even though if they have the same scalar product. You see? Which is the, in some sense, in quotation mark, good one. Good one means that it allows you to obtain natural, non-trivial results. It's a kind of mathematics that is in which the difficulty is to understand the good formulation of the problem. And once you have understood, then there are difficulties to prove the theorem. But there is a preliminary conceptual difficulty. Okay, so now I fix the real part. I know, as I said, that adding an arbitrary skew adjoint, so I have no constraint, so I have the n scalar product. So I have the full structure. Because if I have the n scalar product, I have the adjoint of eta n. And so I can iterate the induction construction. This is what I gave here is a simplification of the proof. If you read our paper, it is much more complicated. But preparing these lectures, I found that the proof can be highly simplified. And this is what I told you. You see. Of course, I told you the main line. Now you have to check a posteriori. Once you have done this construction, you have to check what you have done. Once you have done this construction, what is the result of this construction? As a result, we obtain an interacting Fock space. That is, we have a sequence of Pn, each one with its own scalar product, and we have a sequence of operators A daga n, A daga j n restricted to n, A0 j restricted to n, and A minus j restricted to n. This is the result of the induction. Once we have this, we define once we have this, we define, and notice that in this inductive construction, A minus j n is A plus j n minus 1 adjoint. Once you have this, you define A plus minus j is the sum over n of the A plus minus j over n, and you define A0 j is the sum over n over A0 j restricted to n, and by this construction you define, by the way, of course, you have to define a full scalar product, but this is uniquely defined by the condition that the restriction on Pn is the n scalar product, and the prescription that Pn is orthogonal to Pn for m different. This gives a unique scalar product on P. So P becomes a pre-Hilbert space.
So there is one step there, we don't know the number of solutions.
We don't know.
And another place it is just arbitrary.
Arbitrary scalar. Arbitrary is good for us,
yes,
because it's analog of one-dimensional
Yeah,
case.
yeah. So
The new point is this first step. That is why we need to parameterize the first step.
Arbitrariness is in the real part of it.
yeah.
In the real part of it.
The arbitrary part is very good, because it's a very good analog to one-dimensional case. The new point, which creates troubles, is the A0. The fact that there are relations between the A0, which is this, and between A0 and omega, which is this. These do not exist in one dimension. Once you have the scalar product, remember that by this summation, since we at every step we have defined a dagger, when we sum over n, we obtain the quantum decomposition of the coordinates. Okay? But since at every step we have this adjoint and this is self-adjoint, this implies that xj for the scalar product, this constructed scalar product is self-adjoint. And then by the theorem that we proved in one of the first lectures, this uniquely implies there exists a state such that for any two polynomials P and Q, we have this. And so we have reconstructed this.
And the xj and xk commute. Xj and xk.
The xj and xk commute because by construction, very good remark, by construction we have obtained that these equations are satisfied for every n by construction, because we have solved, we have constructed our objects so to satisfy this. Therefore this equation is satisfied, and this equation, and they are equivalent to the commutativity. That is the construction from where the inductive construction.